Okay. Good morning, everybody. Welcome to another IREE community meeting. This morning we'll have Benoit taking up on some of the things we almost got to last week, and we'll discuss on the IREE's built-in kernels, as well as how microkernels fit in with IREE's compilation flow. With that, Benoit, off to you.
Thank you, Jack. Oh, that's some echo. Need to take care of the echo. I don't know. My mic is disabled, is muted on my laptop. So I don't know what more I can do.
Turn the speakers off as well?
I think I just muted you. Try.
Yeah, oh, sorry. I get it. It was the speaker on my laptop. Okay. Okay, so we're off. There you go. Okay, so here are built-in kernels. Okay, so what's a built-in kernel? It's just a function. Like, as the first approximation, let's say it's just a C function, except you can implement it however you like, as opposed to something that's generated by IREE compile. And the interface is memory to memory. So it's a C function, or like something with the interface of a C function that implements an op for some definition of an op in some dialect, with a memory-to-memory interface. So, like, this is a dummy example for an element-wise add on floats. It would be literally this one-liner, except that you could then also want to provide some optimized versions. It is currently part of the IREE runtime. Or statically linked into Cogen. Thank you, Ben. Yeah. Thank you. So I prepared this slide over the past hour, this whole slide deck over the past hour, and then I sent a link to Ben 10 minutes ago. So I'm going to run into all the fixes that Ben made with you. So being handwritten can be motivated by either performance optimization or targeting targets that don't have an LLVM backend. We'll get more into the pros and cons later. They reside in the source directory in IREE. Oh, sorry. When I click, it moves slides. Thank you. It resides in this directory here. And Ben wrote a nice README there, which you could read. And I call these things kernels. Most people call them microkernels, but before I call them microkernels, I would like to ask, if this is a microkernel, then what would be a non-microkernel? And I honestly don't know. So if you want to discuss that now, we can do so. But otherwise, I'll call them kernels.
I think the intent is these operate on much smaller portions of the data than a normal kernel would, with a much more restrictive interface than a normal kernel would normally have. And so these are designed to effectively operate on the CPU's case, like L1 cache, as opposed to the entire thing. And so what that means concretely is that things like parallelism, in allocations, and anything you would normally do in a kind of heavyweight kernel processing a lot of data happen outside of this. This is the innermost loop inside of some loop nest or parallel system or something like that. So I think that's the micro data, I guess, maybe micro working set.
I see. Okay. So how do we call kernels? So the idea is eventually we could call them from anywhere that we have a use for them, such as, for example, Cogen, in the middle of Cogen, where everything else is otherwise generated by the compiler. We could have, for some specific things, a pattern that would insert calls to those built-ins. However, at the moment, the only vehicle for these kernels is the VMVX backend. And even then, you have to pass a non-default flag to enable those microkernels. So the IREE compile flags are given here. And the way it works is after bufferization, there's a pass called lower lineage microkernels that writes lineage ops to VMVX ops. It has to be after bufferization, because the whole point of this VMVX ops is to be a trivial mapping to the built-in function core. And the built-in function pointers And the only way we can give it a pointer is if we're already past bufferization. And then there's a bunch of convert VMVX to VM patterns that will write those VMVX ops to VM.core ops.
Yeah, so what's important there is VMVX is one consumer of the microkernels, and we will have more of those, CodeGen being the big one. And today in CodeGen, we are doing something similar to this. So for things like libc calls that LLVM insists on omitting, like floor F sometimes, or float 16 to int16 kind of conversions, we currently emit those offline and then link the bit code in statically into the CodeGen. Statically link them in, let LTO run, inline them, dead code strip the ones we don't use, and that's what ends up at our final CodeGen shared libraries. The idea here is we basically be doing the same things. Instead of libc calls via muscle, they would be these microkernels that we would be writing. So we do at least have most of the infrastructure in place for that, but currently VMVX is the only consumer of these. So I think previously there was VMVX was microkernels, but it really is just VMVX is one way to call the microkernels. CodeGen would be another way.
Yeah. And for those who are not familiar with VMVX, it's basically when you do IREE HAL target backends VMVX, you get something that runs in a bytecode interpreter. Well, like by default, there's going to be a bytecode op being dispatched for every single scalar operation in a model, so that the default is really slow. But the idea is that with the microkernels, we take the slowness out of important ops one by one, and maybe even one day VMVX will be fast enough to use in practice. So yeah, why do built-in kernels? So each has pros and cons. Actually, like it's depending on the audience. The most typical question is either why built-in kernels at all or why CodeGen at all. Like if I talk to my friends who the other people working on handwritten neural network frameworks, they ask like, why do you do CodeGen? And I do fully expect that why do kernels at all is also a reasonable question. So the idea is that we don't want actually to advocate for one over the other as being better than the other. Actually, we do plan to combine both. Something that we probably envision is that on say AR64, we could have a module that has a built-in kernel for matrix multiplication and maybe one or two other critical ops, and then CodeGen for everything else. But it's also fine if you don't want any microkernels at all. And it's also fine if you have an exotic target for which there isn't even LLVM backend. And then microkernels can offer a way to target this kind of machine. So it's going to depend on, yeah.
I like the way you frame that, because it really is the equivalence of like nowadays when it's like, why write C at all? Why not just write assembly? Versus, why only write C and never be able to use inline assembly? And any complex project, will end up with both. And I think that framing is really good.
Thanks.
One important thing to keep in mind is we will likely never end up in the case where we never do CodeGen, just because that's really hard.
I think it's fair to say that part of the motivation for something like IREE is that, like, we all come from the background where we spent a few years dealing with pre-IREE, pre-compiler things that were like libraries of kernels, like TensorFlow and things we used internally at Google before TensorFlow. And I personally spent years maintaining this kind of library of kernels approach. So I have like painful direct experience with how hard that is to scale over years. So yeah, CodeGen is needed, but sometimes built-in kernels can be useful too. So with that out of the way, we can still enumerate a few specific pros and cons of kernels versus CodeGen, so that it's clear that we are not advocating for everything replacement. So kernels are good for exotic targets without LLVM backend. Yeah, that's true. We mean like typically some accelerators, maybe some. You could be the hardware team designing the new chip from scratch. So that isn't an LLVM backend for your chip because you're the only person in the world who knows your chip, and you can have a chicken and egg problem between software and hardware there. Optimal performance, sure, like there will always be some cases where it's easier to get optimal performance out of handwritten assembly than to write the CodeGen patterns and fix any issues you run into with CodeGen with performance. It is totally possible to generate absolutely anything with CodeGen, but with sufficient effort in engineering on the compiler side. So sometimes, for some people, it will be the better compromise to handwrite assembly. And then I mentioned also, Suraj, does this enable reasoning about fusion involving both kernels? So actually, Ben, do you want to take this one?
Yeah, so it depends. So when we are linking these into CodeGen and we're statically linking them and we're doing a full LTO pass, it is possible that LLVM might magically be able to do some detection and do some fusion there. But the intent mostly on these is they're just like C calls, and so it'll be memory to memory interfaces. And so a fusion there would mean a unique kernel that, if you had two lineal jobs, matmul and add, you would have a matmul add kernel or a matmul kernel that could add, as opposed to the expectation being that there is a matmul kernel and an add kernel, and those end up fused in some way automatically. Again, LLVM, when we're linking these all together, might be able to do that in some cases. But the other thing this provides, and just on the performance thing that's really nice, is predictable performance. So if we handwrite one of these kernels and compile it, it will always be that kernel and work that way. Versus in some of the cases with CodeGen where you can fall off performance cliffs if things start to fail to vectorize or you spell registers in weird ways or things like that. And so even if sometimes there are benefits from getting fusions performance-wise, if 99.9% of your model time is spent in 4 different microkernels, having those be consistently good in all cases, regardless of the model, is an interesting use case.
I have personal experience with that because I spent years at Google writing library of kernels, neural network inference frameworks, and their matrix multiplication backends. And I never fully optimized to 100% of peak. I always struck some compromises with generality. And then XNNPAC, I came along. XNNPAC is another Google open source neural network inference framework. And the XNNPAC authors were way more serious than I was about squeezing the last percentage of peak performance out of the kernels. And basically, whatever my architectural superiority was actually insignificant compared to squeezing 10% more out of the kernel. Now, so Kojo, so basically, as we are currently designing these microkernels, they are a memory-to-memory interface, right? So that's basically a hard compilation barrier. Like there is no compiler that will remove these memory loads and stores that we have at the beginning and at the end of these kernels, right? If we wanted to change that, we would have basically to stop writing kernels in assembly, sticking to writing them maybe in C with intrinsics, combining with LTO, something like that. So that's a theoretically possible future thing, but the microkernels that we are discussing today are plain code, memory-to-memory, straight fusion boundary. That means that if we try to fuse something, we have to know what we want to fuse, and we have to fuse it before we go to rewriting to built-in kernel ops.
Yeah, because as soon as we would go to intrinsics, we'd effectively be just like normal CodeGen.
Right. So there were multiple questions. Okay, I just opened the conversation panel. So Morali has a question. If we just target VMVX, we can either lower that further using more passes or directly generate new kernels. The decision on how to lower VMVX could be made later, right? Ben?
not sure I understand necessarily.
I mean, why do we have to decide it has to be microkernels? Why can't we just target VMVX, which has interfaces for microkernels, as well as potentially other things like simple loads and stores or whatever, and then we can take the VMVX code and do one more cogent pass from it to either target normal CPUs, or we can target microkernels directly.
So VMVX, the VM that we're running on, whether that's our bytecode VM or we're emitting C code via the emit C dialect, is a inherently scalar architecture. And so we effectively, as we're lowering from linalg, go through just enough to get those microkernels out and then go straight to scalar form. So it's not easy or viable to ever go back to a vectorized efficient form from that. When you want to do that, that's what the full cogent path is for. That goes through the vector dialect and does additional levels of tiling and things like that. So when you're going to VMVX, you're basically saying, I want to run in a ultra portable, no executable code required at runtime kind of environment. And the cost of that then is that you lose the performance benefits you get from the codegen side of going to vectorized forms. Once we're able to link the microkernels into both codegen and VMVX, then you don't have to make such a binary decision as to, that thing. Importantly, everything up to the point that we actually do this is the same between both paths. And so in general, any model that we can compile via codegen, we can compile and run via VMVX. It's kind of our reference backend. And so as a user, you wouldn't see a difference between something running and not in either configuration. It's really just, is your deployment scenario such that you want to ship a binary file that doesn't need executable pages at runtime, or do you actually want full performance and what that entails? Does that answer your question? I'm sorry.
Somewhat. One follow-up question. Sorry. What is the thing which gets lowered to microkernels? As in, what's the layer after which you generate microkernels? I guess that was what I was meaning, not VMVX per se.
Do you have an example of any IR in here, Benoit?
I can follow a link actually. I have.
We can also take it offline.
Yeah, sorry, I don't have an example IR here. It wouldn't be particularly enlightening. What are you looking for?
No.
Was
Maybe
just
I
seeing
can-
if you had the dialects or something.
Maybe I can just answer this question quickly. So I think currently it's being handled at the linalg op level after bufferization because it's a memory-to-memory interface. So that's the current implementation. There might be a place in which you could do it earlier, have a representation of this goes to microkernels without bufferizing it, and then manage it so that after bufferization you do call the same kernels, but that's still a little bit farther out. We need to explore that a little bit more. But right now it's a linalg op after bufferization and before vectorization.
And Thomas had a question too.
Right. I mean, it was follow-up to basically you were saying it has to be a memory-to-memory interface, or it is right now a memory-to-memory interface, and that prevents fusion. But is there any reason why we cannot just make it like a register interface so that we could actually fuse things?
Two major reasons would be that, well, a couple. So one is that if there might be a layering in here. So if we have to call this from something like VMVX, it has to be memory to memory just because there are no registers. And so we could have two layers of one that was presented a memory to memory and then one that was lower level that was used by it that did vectors. The tricky thing that exposes it, and I think Benoit touches this on this in some future slides, is that breaks the insulation of target architecture features. And then also in a lot of cases when you're writing these microkernels, one of the things you actually care about is your register placement and where you're loading registers and where you're storing registers from. And exposing that on the interface basically takes that control away from the microkernel. So there is a world where you could imagine a decomposition of these if you had like load and store microkernels as well as mapmel microkernels, and effectively something that looked a lot like the MMA kind of stuff. But that gets fairly complex and then starts to edge out of the territory of the predictable performance of handwritten code and more into generic code gen.
If I had to do it, maybe the way I would do it would be to go to inline assembly. Like so far, I've been writing C and out of line assembly. But if I wanted to retain almost all of the characteristics of out of line assembly and expose a register interface, I would do LLVM inline assembly. You know, it's actually exposed in MLIR inline as an op, I think, thanks to Nicolas. And I've been using that before starting working with kernels, and so we can have a inline as an op that it takes actually a vector SSA variables in and out as registers within the inline assembly snippets. And yeah, we could do that. We don't usually care about the placement of the in and out registers within the register space. Most architectures, all registers are equivalent for these purposes. So why not? But it would be a bit of an investment to, like, it's way easier to just have out-of-line assembly 5. It will also be friendlier to the typical hardware team wanting to port to their target. So that's probably why we haven't done on this.
Yeah, we also have the advantage here of like at the granularity that we're looking to use these at, they wouldn't be like a single element or 8 elements or something, but ideally, hundreds of elements, if not more. And so in most cases, you wouldn't have potentially enough registers that wouldn't clobber in order to do that.
So, I got that. Actually, no, that's the key. And actually, let's give an example. We're going to get into that. Sorry, go ahead, Matt.
In a way, it's an API. All machines ever are going to have a void star. Some machines will have 64-bit registers, some will have 512, some will have 256, and we would have to capture that somehow in an abstraction to make that work.
Right. And the other element I wanted to draw attention to is, imagine your kernel is computing a small tile, a register size tile, like maybe 8 by 8, if that's how many you can fit in registers, in a matmel. Okay? So the output is fixed size, say 8 by 8. But the input has a dynamic k dimension. That's the number of iterations of your innermost loop. And you have this dynamic dimension that basically means you've got, at least on the input side, you've got to consume a memory input, right? If you say, I want register input, then you can't have this loop as part of your kernel anymore. And you're back to the way we're doing it in CodeGen, where we have a vector.contract and we lower that to intrinsics or something like that. And like basically we're back to, like, this is a big topic in itself, basically the issues we run into with vector contract lowerings, but basically requiring a vector register only interface also for the inputs would make whatever we're doing equivalent to vector contract lowering.
Right.
Yeah, output vector might be interesting.
But you could, take
potential
memory.
feature.
Yeah, exactly. Yeah, because usually you want to fuse with the output, right? So that.
That's a good idea and something we can definitely explore, because besides things like a scatter or something like that, we can generally do that. The hope for a lot of this, and one of the reasons why these are kind of sized at the granularity that they are, is that we're staying in at least L1 cache. And so it's memory to memory, but hopefully because the entire problem space has been distributed and subdivided, almost all of these, at least especially on their output, are writing into L1 cache. And then if in CodeGen, as soon as it returns from the microkernel, it's either calling into another microkernel or doing vector loads to perform some CodeGen stuff. That's all going through cache. Hopefully it's all write combined and it's right through caches. And so hopefully everything's pretty good. But it's at least better than a kernel interface on an entire problem size where, if you have 2 element-wise kernels and it was going through a megabyte of memory for each one of those in a loop, you'd be cold caches the whole time. Here, once we're distributed on multiple cores, each core has its own local caches, and hopefully we treat the memory subsystem a little bit better in those cases.
Suraj had another question before he leaves. restrictions on how the kernels are presented. Just C++. Can it handle letters that I don't know? I don't know what BYO is. So go ahead.
bring your own. So yeah, we have a couple different ways that those things can come in. The tricky things once you get to something like SPIR-V or GLSL or something like that is that they don't have a very good linking story at all. And so generally, you'll end up with two kinds of things. You'll end up with like a header file equivalent that you want to bring in that you can call. And I think that's roughly the equivalent of what we're talking about here. So it would be, you could bring functions, snippets of GLSL or SPIR-V or something that you could link in as to the code gen. The other case is entire kernels. And those are trickier because kernels then have interfaces and expectations around bindings and IO and stuff like that. But I think for the case of the kind of times in an OpenCL kernel where you pound include something, this is basically that. So we could offer a similar interface in the GPU backends for that.
Okay, should we continue with the slides? So we weren't quite done with this one, but I think we basically covered it by talking. The trade-offs mentioned in the middle of the slide, yeah, sometimes you could do something very well in CodeGen, but it would require, making the compiler code a bit more complex or a bit bigger, and just for the needs of one particular target. So sometimes if you have one target that has very specific, requirements due to its SIMD ISA details, then actually storing a kernel at it is a way to prevent those SIMD ISA details prevent those details from making the compiler more complex for everybody else. Sometimes it's a matter of code complexity, but sometimes it's also about insulation of target details, and we'll have an example of that in a later slide. Kernels are bad for what CodeGen is good for, so fusions, we discussed that. And scaling to all the ops across all the targets, this 2D matrix that has been held for the library approach that people like me were working on before joining IREE. You have 1,000 different neural network operator types. You need to target dozens of different target architectures. This doesn't scale. CodeGen scales. Kernels inflate the error runtime to the extent that they are part of the error runtime. Ben had edited my statement earlier. It can also be statically linked in the model. So that also means a constraint. When we write kernels, we have to optimize for code size, not just for performance. We'll see that later.
Yeah, part of that is just selecting which things actually get kernels. And part of the hope is by being at kind of the microkernel interface where we're still inside of a loop running from CodeGen that CodeGen is driving, that we have an opportunity to decompose these things to the point that we have on the order of dozens as opposed to on the order of hundreds or thousands.
Renato says, go ahead, Renato.
No, sorry. It's just I got on this slide. I haven't seen the previous slides. We're just talking about big kernels, right? Why they're bad, not the microkernels.
We're only discussing one kind of kernel at all. Some people call it kernel, some people call it microkernel, but we're discussing the flavor of kernel that we are adding to IREE at the moment.
Well, because the whole point of the microkernels is that you have the power of the CodeGen to block tile and do all of your transforms, and the power of the microkernel that is just to call in that 8x8 block or something that is efficient in cache and etc.
And okay. So that's basically why Ben calls this a microkernel. That's what we're doing. We're doing microkernels.
Okay, perfect.
I didn't know the terminology, so I just shortened that to kernels. But now that I understand that it actually means something to people, I will edit this and put the use in front of the kernels everywhere. Thank you.
Yes, because if you're writing like a CUDA kernel or an OpenCL kernel, is a giant thing that only works for that one problem in that one GPU. So
okay. So that's where the terminology comes from. Okay. I'll just add the use everywhere. Okay, we do mean microkernel everywhere.
Perfect.
Okay, so yeah, next slide. Okay, so kernels insulate target details. That's one potential pro of kernels that I mentioned on the earlier slide. So kernels have a memory-to-memory interface. So that's the trade-off. You give up on fusions And in exchange for that, you get to insulate a lot of SIMD details. Actually, you get to insulate all of the details except for the data layout. And then on that point, even data layout, you get to insulate some of that due to the next point. When you write a kernel, a microkernel, you can put the boundary for your microkernel anywhere you want in the loop list. You can decide what's the boundary between what's part of the kernel and what's the outer non-kernel code calling into it. So you can, if you need to abstract a little more data layout stuff, you can actually make some data swizzling, some data relayouting, part of what your kernel does. And you can do that while retaining good performance because you get to choose the boundaries. So you get to put just enough loops into your microkernel to amortize this kind of swizzling. Often, like in the case that I ran into, as I described here, just the innermost loop being in the kernel was enough. So here's an example. ARch64, so that's ARM64, with a recent SIMD extension called i8mm. It's implemented on the Apple M2, I've been told, and it's implemented on the new Qualcomm source, new mobile ARM architecture CPUs starting from end of last year. So in particular, I have a Moto Edge X30 recent device. It's less than 1 year old. It has a Snapdragon 8 Gen 1 SoC, and that supports this extension. And this extension does a 2x8x2 matrix multiplication. So the left-hand side is 2x8, right-hand side is 8x2. And the accumulator is 2x2. And that's not the first time that we have SIMD instructions specifically for speeding up some matrix multiplication. But it is the first time on ARM that we have an accumulator register that is itself a matrix with a size of more than 1 in both dimensions. For example, before we had dot product extension that was 4x4x1, so it was a matrix times vector, but the accumulator tile was still a vector. Now, for the first time, the accumulator tile is a matrix. That's going to be the norm. ARM SME goes way farther in that direction, and looks a lot like I'm not familiar. Anyone who knows GPUs?
Yeah, it does a lot.
Right. So I think that's about my point. Everyone is going in the same direction of true matrix multiplication instructions. And that includes GPUs, like you say, and that includes ARM and everyone. So what does that mean for how we abstract that in either a codegen or kernel approach? I actually wrote a vector.contract lowering to inline assembly targeting this instruction 6 months ago. But then, because my vector contract was 2D, it was like a vector contract on 2D vectors representing the LHS, RHS, and accumulator matrices. So they were raw major matrices. And so the vector swizzling had to be part of the vector contract lowering. Now, it would still have been possible to have further codegen patterns sorting that out and still obtaining optimal code for this case. But it would have required writing more patterns, and it would have required not writing this this lowering in inline assembly. Oh, thank you, Renato. Yeah, this is exactly what I'm talking about. So instead, by having a microkernel, I can say, oh, my microkernel generates a 8x8 tile. And yeah, the 8x8 tile is raw major as far as at the interface of the microkernel goes, but the microkernel will internally do the swizzling. And why is it suddenly low overhead while it was high overhead in vector contract lowering? It's because the microkernel contains the whole inner loop. So we only have to swizzle at the very end of the loop once. That's exactly why earlier, and we discussed the importance of having dynamic sizes, and that implied having a memory interface instead of a register interface. It's only by having memory interface that we enable dynamic sizes that enable putting the whole inner loop in the microkernel, that enables amortizing this kind of swizzling, and that enables hiding this kind of SIMD micro detail as an implementation detail of the kernel.
The other thing this really, it like kind of highlights what this whole system is designed around is the compiler. When we're talking about these microkernels, especially when they're plugged in at runtime dynamically, we wouldn't be able to generate code that knew about these 8x2 and 2x2 and values like that, because that would be a leak of the ISA details all the way up, and then we wouldn't be able to plug this in and run the same exact program on a different architecture. And so a lot of what we're going to need to do in the compiler, when we talk about things like propagating, packing, and padding and things like that, is padding to the minimal or the maximal common dimension of these things. And so whether that's 8x8 or 32x32, that is what the compiler will be producing. It'll be passing those pointers into the microkernels, and it's up to the microkernels to have that inner loop based on their architectural details. So something ARCH64 with I8MM, might have a certain number of loops producing these 2x2 tiles versus, a generic ARCH64 without this extension, which would still produce, the same output size, but might have to loop a couple more times to do that. The important thing being the interface as exposed to the compiled program is effectively the same, regardless of how it's actually implemented under the covers. And there's definite trade-offs there, but when you're in this space and you're not doing code gen, that's kind of the trade-offs you come up with. Go ahead.
To complement that, I totally agree. In the previous slide, we're saying that the compiler will be too complex. I think this is not the job of the compiler at all. Because the way you would lower this is you would see an instruction. Oh, this is a matmul. I'm going to lower into this huge loop of instructions, and that doesn't scale, right? That doesn't work with register allocator, with anything. So it's not a thing that the compiler can actually do and should be doing. So the only way to go is to have microkernels and just expose the ranges and the sizes and the shapes and the tiles to the compiler, so the compiler can call the right microkernel at the right point.
Well, and I think the important thing here is, as much as possible, define the interface such that the compiler doesn't have to know. In a lot of cases, those things.
Exactly. Yes.
Just the minimums.
Yeah.
It's a tricky balance, and there will be these cases where we end up with, and that's, as IREE is a toolkit, if you as someone coming in to use IREE know exactly which platform and exactly which architecture and stuff, you can very narrowly specify that, and you can end up with the minimal possible padding required and wasted memory and stuff. Versus I'm just a random user who wants to upload a model to the internet and allow people to run my person detector model or something. In which case you'd go conservative for that.
It's worth pointing out, though, that for all the detail insulating capability that kernels bring, we're still leaking all the way up the higher level of tiling, like 8x8 in this case, like here. Well, we're not leaking the 2x2 micro detail tiling, but we are still leaking the 8x8 tiling that corresponds to the register space level tiling. That is a whole separate topic. So we're not saying that we're solving that particular topic here. Here we're just saying we are putting a barrier to prevent this existing leakage of ISA details from getting even worse.
Yeah, and it helps here thinking of the hierarchy of these things is, as we go higher up the stack, the granularity of memory that we care about goes up as well. And so, at the highest level, we're caring about megabytes, and then we're caring about, hundreds of kilobytes. And at the point here, we're really talking about the details around a kilobyte or so of data each time. And so the concerns, and how far that is allowed to leak up, it's fine if it doesn't leak all the way up, because when you're talking about a 10 gigabyte weight tensor, the exact swizzle details of 4 elements on the innermost dimension are kind of moot.
Yeah. Okay. Let's go to the next slide. Okay, so an example is basically the only microkernel that I've fully fleshed out, and only on ARCH64 plus the generic code. But it gives me an example to discuss. So MMT4D stands for matrix to matrix multiplication transpose. Matrix transpose, that's computing A times transpose of B. So it's like matrix multiplication, except the right-hand side is transpose, and we are transposing the right-hand side because it helps implementations of matrix multiplication stay a little simpler. But otherwise, think of it as just matrix multiplication. 4D is because this is a tight layout math model because it's meant to be efficient. And the way that we represented the tile layout initially has been by using 4D tensors. Mahesh and Han are working on a more modern way that allows to represent tile layout math model without immediately going down to the details of the 4D shape. But basically, think of MMT4D as just matrix multiplication kernel on tile layout data. And by kernel, I mean not including the packing and unpacking work to go in and out of that tile layout. So far, only AH64 plus a couple of variants, plus .prod, plus i8mm. Optimized for code size, for the reasons said before, while still trying to be at 95% of peak. Another constraint is this has to handle both the accumulating math model operation, C plus equals A times B, and the non-accumulating case, C equals A times B. Because on the one hand, lineage ops are perfect loop nests, so they are accumulating into existing accumulator values. On the other hand, the vast majority of practical math models in ML applications are plain math models. So in practice, the accumulating lineage math model is typically used with an accumulator that was just before filled with a lineage.fill with zeros. And our microkernels have to do both because we want to support the fully the general case of lineage math model, but we also want to be a little faster in cases where we can be. And this needs to stay simple, easy to port, easy for anyone to hack and port to their target architecture and generalize to other operation types. So yeah, I just got into this topic of to accumulate or not to accumulate. So since I've already said it, I'll skip that slide. IREE ukernel MMT4D, or maybe I'll follow my link here. Actually, share this stuff. Okay. Okay. So see, it's just the entry point. So the high-level work it does is it validates the parameters, and then it tries to see if there's some early return path that corresponds to the cases where one of the dimensions is 0. And that's also where you would slap your own custom code for a port where you want to take over the whole implementation. Otherwise, we go through our generic path, which consists in selecting a so-called tile func. So this function returns a function pointer, or produces a function pointer in this out parameter to the function that will compute one tile. That's the function that we typically want to write in assembly. And so that function has only one dynamic dimension anymore, which is the innermost k dimension, and everything else is fixed size, say 8 by 8. And then we go through. We're going to the generic loop nest implementation that will call that tile function for the innermost loop. And so that's a single function that implements, MMT4D not only for all SIMD ISA variants, because that's abstracted in the tile func for all, tiling parameters. That's also a part of the params, and even for all data types, because since all the arithmetic is inside this tile func behind the indirect function call we're doing here, there is no actual arithmetic in this function, so it can be completely type generic. Even like float versus int 8, the only thing that matters is the size of. So that's how we achieve a good compromise of performance with code size. I do understand that it would be a little more efficient if we could specialize this function fully to each case.
Yeah, and one of the things, this is where when we're statically linking these in and able to perform LTO, LVM is, at least as long as we do it right, pretty good about propagating those function pointers. And so it should end up being able to specialize those based on compilation settings of, code size limits and stuff like that. So I think this case is, for the dynamic, fully runtime, specialized, kind of architecture agnostic version. And then the stuff we'll do later on as we get this linking into CodeGen, we should be able to make the overheads that are there go away.
Yeah. So I'll show you now a couple of assembly implementations of the tile function. Well, maybe I should show you the generic C code first. But anyway, like you can imagine what the generic C code looks like. So this is a dot product. So AR64 plus dot product case. That's the inner loop. So you see what it does. This is the loop counter decrement. This is loading LHS tile. This is loading right-hand side tile. And this is the multiply accumulates, register to register. There is no stores to destination in the inner loop. The stores to the destination occur only at the end of the function after the end of the inner loop. So for this particular case, it would be perfectly possible to achieve a similar result in CodeGen. On the other hand, it gets more interesting for the I8MM case that we discussed earlier with this 2x8x2 instruction that has the 2x2 internal swizzling. So here, that's where it becomes a big deal whether or not we accumulate into existing values or we can just clear the destination. See, we do a test and branch on the flag that tells us whether to accumulate. This is a non-accumulating case, with just 0 registers. That's easy. This is the accumulate case. So we have to load the existing accumulator values, and then we have to swizzle them into 2x2 layout. So that's more expensive, but it's still not too bad because that's done once before we enter the inner loop. And so this function looks a little more complicated because I have optimized it a little more. I basically did a 2x partial unrolling to use all of the register space to maximize load to use distance. But basically, you get a typical matmul inner loop where you have a lot of arithmetic. Those are the matmul instructions. Each of these instructions does 2 times 8 times 2 multiply adds. That's 32 multiply adds per instruction. And this is loading data from the right-hand side, and this is loading data from the left-hand side, and so on. And at the end of the inner loop and all its epilogue stuff, we're finally, sorry, that's the epilogue stuff. At the end, we are unswizzling back to a raw major format and storing to destination. All right, so let me go back to the presentation. Yeah. Oh, go ahead. Is there?
Oh, sorry. I thought I had seen someone's hand up, and I was trying to find out where to view that in the interface. Did anyone have a question? Is there a question?
Yes, I mean, I just had a quick one. In the Microkernel example you showed, you have a validate function at the top. What is sort of the expectation with respect to what validation will be happening in the compiler versus in the microkernel? Do we actually expect the compiler generating these invocations to catch the majority of these, or are there also some cases that we have to do a runtime check for?
Yeah.
Anything that affects correctness is something the compiler should do, because we should be able to, in a lot of cases, statically figure that out and remove them. Anything that changes runtime correctness, so memory safety and stuff, must happen on each call, just because that's, you know, the whole point of this case through VMVX anyway is that you're running in a slightly more secure environment with memory checking and stuff. So I think that's a big difference. And then again, when we're statically linking and there's LTO and, you know, it can see all the constant parameters from all call sites, it should be able to fold away a lot of the checking we're actually doing.
Yeah.
Does that answer your question?
Yeah, to be clear, by validation, I also mean just plain assertions. You know, even if it's the case that the compiler should only generate valid calls, and so any assertion I put on the parameters should never fail, you know, I still want to have the assertions. They still need to be somewhere. That's basically what I call validation. So in a sense, there's some release assertions there like that. Like, not assertion because they just cause the function to fail and don't abort the program, but basically there's some checks there that may not be technically needed, but they have completely negligible overhead, so I didn't have a reason to take them out. So Yongji has a question. Do you want to go ahead?
So I joined them late, but how is different from intrinsics, right? If you write all stuff in assembly, so it looks to me it's more easier if you program in intrinsics.
Yeah. So for a good reason, so It is possible to write any of that in intrinsics. The question is, what's the likelihood that the resulting binary will be just as efficient? It's very hit and miss. Sometimes it is just as efficient, and sometimes it is not as efficient. The leading cause for not being as efficient is register allocation issues. Let me share again the tab with this kernel. So the key place is, yeah. See, so this kernel was 2x partially unrolled to maximize use of all available Cindy registers to maximize load to use distance. That makes this kernel the hardest kind of code to register allocate for in the compiler, because there's only barely enough registers in the architecture to allocate all of these local variables. And that's assuming that the compiler did not perform some kind of optimization, some kind of code reordering that increases lifetimes of local variables that would turn this hard but feasible problem into an infeasible problem. And in my experience, that happens very often. That you write this register-tied C code assuming a mapping between your C variables and registers, and the compiler defeats you with some optimization that increases register pressure, or in some cases, even without increasing register pressures, somehow fails to get a good register allocation. There's a typical way that actually this increase of register pressure occurs in CodeGen is when some patterns introduce some temporaries that technically adds more local variables, so adds register pressure, but the intent is that they should evaporate before register allocation, but something that is enough to confuse register allocation in register type case.
And with the register allocator trying to find a fixed point, it might, just spiral out of control rather than find a fixed point and then say, I gave up with this horrible code that I found. I'm going to stop here, and it's horrible. I'm not even going to go back to the beginning where it wasn't that horrible. I'm just going to stop here.
Yeah, when you end up with 20 spills and loads on your inner loop, it feels bad.
Yeah.
So we have 2 minutes left, so I'll just show you some results. So those are benchmark results for this i8mm kernel with the with the 2x partial unrolling. If you want to see results with and without the 2x partial unrolling to justify this partial unrolling, you can click the results link here. It has the details. But the summary after this optimization is that so this is on my phone that I use as my go-to Android test device, a Moto Edge X30. It has a Snapdragon 8 Gen 1. There are 3 CPU Cortex. The little cores are Cortex A510. The big cores are A710. And the big macho cores, just one of them is a Cortex X2. And the A510 are in order, and they perform 1 SMMLA instruction per cycle. The A710 and X2 are out of order and perform respectively 2 and 4 such instructions per cycle. That's why you have this large discrepancy in the peak GOPS. Go ahead. No, someone asked a question. No, okay. And code size, so the total is 3.5 kilobytes. And the breakdown is this 2x partially unrolled i8mm kernel is bigger. It's 700 bytes. That's exactly 4 bytes per instruction on this architecture. A simpler .prod kernel is only 200 bytes. The generic kernels are 500 bytes each. And so, yeah, we have a small total.
Yeah, and I think this shows the kind of granularity of where the microkernels sit in the hierarchy and how we can think of things where we might have 60 microkernels at some point one day for all the different kind of cases we want. But we'll still probably be talking about tens of kilobytes of code there as opposed to megabytes or tens of megabytes of code in larger kernel-based libraries.
That's what I have. And, Lorenzo has a question.
Oh yeah, sorry. Yeah, I mean this question is a little bit more long term. So, the main problem with this microkernel things is that so most of them, for instance, require to have a specific relay out your tensor in a specific way or something similar, and so they are not really completely transparent to your codegen. So essentially, also your codegen should be aware that you are going to target this microkernel to sort of relay out your tensor in a decent order. So how do you plan actually to address this issue here? Because it's not so easy to do. These relayouts are quite expensive, so you actually want to try to sort of hide as much as possible doing these things. And so you end up sort of having a code generator that also need to take into account this relayout and propagate through all the network topology.
Yeah, so totally agree, and I think that is one of the reasons why we treat this stuff like we do, which is that very early on in the process, we need to know what we're doing things for. But at that granularity, we don't yet need to know the exact tiled layout. The only thing you need to know is that the data is going to be consumed by one of these microkernels, and the only thing you need to know when you actually go to pack it is that it has to be consistent. And so if you're packing, if you have a pack microkernel and then you have the matmul microkernel, both of those need to be consistent, but from the thing actually calling both of those kernels, it doesn't care. It's just passing around pointers. And so the architectural details are still lower down and hidden in these microkernels. The transformations we do at the higher level are really about moving where those calls happen, such that packing happens in the producer of data before we write it back into memory, and then consumers consuming it pull out that pack data. And as long as they're consistent, then it works. And this is similar to how optimal texture layouts work on GPUs. You don't necessarily care at any point in time what the actual device assigned the layout to be. You only care that at some point you said to put it from a linear layout into an optimal layout, and then when you go to consume that, you're asserting that it is in that optimal layout, and it pulls it out. You, as the caller of those APIs, have no idea what the actual layout is.
Yes, but for instance, but what does this mean? So let's say that you want to pack your matmul, right? So do you want to, or let's say that your microkernel is bet your matmul in a given layout. So you need to take, relay out first before calling this microkernel, and then you need to relay out after, because otherwise you break essentially all the other operation that use your result, right? So
not necessarily all the other operations, right? So if you're performing an element-wise operation, it doesn't care what the layout is. And then this is where we get into the kind of details of like what we're operating on here in the microkernels is a very localized region of memory. And so if you were to think of the original tensor, instead of being by F32, it was by 8 by 8 by F32, and this is where MMT4D gets its 4D from. The inner 8 by 8 is an opaque, data layout from the rest of the program. I can still transpose a matrix that had 8 by 8 elements, at the global level, and do a 10 gigabyte, transpose, treating each 8 by 8 by F32 as if it's a single opaque element. And so, and then as we propagate those across the program, I can do something like fold that packing into constants and fold that packing into initializers and things like that.
Okay. Yeah.
Even if it's a very far distance away when it's consumed.
Oh, yeah. Okay. Cool. Thank you. Yeah.
One thing we thought about internally, like using the this VNNI packed BF16, is if we have a matrix that is like 2 by 32 times packed BF16, which is just a tuple of 2 BF16. So your type will be a square of 8 by 8, will be your whole type, and then your matrix is a matrix of those blocks, right? So of course this is like tiling, but I think the point is, if this is a multiply channel-wise or width-wise, and what is the row major, column major, and this operation, how does it operate, and where do you put in registers, and etc. So I think there's a lot of knowledge in the ISA and in the model that they have to share a common understanding, and there's so much variation on both sides that is going to end up like this crazy list of attributes, of lists of many things. So I think if you can, perhaps the easy thing is like we do in LLVM, is to say, well, this target has property X, and if has property X, I do this. I don't care what the shape in the end is. The target is telling me that this is a good idea, so I'm just going to do it. right? It's not the cleanest thing ever, but it is a way that you can simplify this middle ground where all of the combinatorial effects are in play.
Yeah, and that's really, you know, Mahesh is putting together some stuff for this now of we, you know, I know there's some stuff happening with the TPP work and stuff with packing. For us, those kind of packing operations are the things that happen inside of dispatches. There is another tier of the hierarchy above that is the packing that happens across the entire program. And you can think of it just as like, you know, at the high level, if you're a user writing some C code, you're going to call a function that packs some data and returns you a packed, you know, buffer of data. You don't actually care or know at that time what's on the other side. And so I think that's the big thing that's kind of been missing so far, is just that extra level of the hierarchy. And I'm really excited for us to kind of get there, because the same things, you know, you mentioned like the packed bfloats and stuff, is block sparsity is exactly the same kind of thing. From a high level, you just need to know what your maximum buffer size is. What the actual consumption of the bits is inside will vary, and it's not even elements at that point, right? It's an index table with offsets with some number of dense elements and stuff, and so that is a completely opaque element from the rest of the system. You know, I can slice and I can copy and I can gather and I can do a bunch of operations on those at certain granularities, like outer dimensions. But if you ask me for like a single element of a sparse block, then you have to do some work that's architecture specific.
There are 2 or 3 outstanding questions, and we are already 6 minutes past the end. Yongshi quickly asked, will assembly be the only way to write microkernel? Actually, no, we had addressed that, I think, before you joined. This is just an example of how I implemented a couple of microkernels. You're welcome to implement microkernels in whichever language you prefer. The only constraint is you need it to have the interface of a C function.
Extern C, yeah.
Extern C. There are 1 or 2 raised hands. I guess go ahead, Manish. You're muted, or I don't know. Yeah. No, we can't hear you. Sorry.
Yeah, I think your microphone might be disabled, and I think actually Benoit, my point was just actually to the one you added as well, where it's like, I think it's, you know, thanks for the presentation. This was actually like really awesome. Just in the interest of time, I think let's carry these over on like the Discord and all the places. I think very exciting. There's a lot of interesting work, and I mean, I love seeing 96% of peak. That's always a nice number to see. You know, thanks everybody. We'll send out the video of this shortly. Well, probably tomorrow. Feel free to add more items to the forum for things you want to discuss. Roughly a month from now is actually the LLVM dev meeting, so exact details of when the next meeting will be, you know, we'll need to double check. But you know, glad to see everybody here today, and see you next time. Everyone.
Thank you, everyone.
Yep.